So in this video, we're going to be covering an introduction to black holes and how they work in general relativity. The goal for this video is to use the math to our advantage rather than getting bogged down by it. We're going to focus on the parts of the math that explain how it works that will be simple to understand. The first idea that we have to think about is that in GR, gravity is indistinguishable from being the geometry of spacetime. We have spacetime as a curved manifold that is a curved kind of surface, and it's described by these lines called geodesics. Geodesics are basically an analog of a straight line, except now we're talking about our spacetime being curved, so they will not necessarily look flat to you. So I'll give you some examples. First one will be a cylinder, where you see these lines that are clearly straight lines on the cylinder surface, but to us living in a flat world, we see them as being curved. And the same thing happens on a sphere here. You have these great circles of the sphere that are geodesics of the sphere, and yet we perceive them as curved. So this is how latitude and longitude lines work as well. So in space-time, we have to think about time is also a coordinate of the space-time just as much as x, y, and z are. And that means that it's going to get bent and curved just as much as everything else does. And so this curved time is going to allow us to explain things like gravity and black holes and so forth. So I'm going to use an example from special relativity that you've probably seen before, and then we're going to cover how that can get extended into general relativity. We're going to look at the line element ds, which is also called the Minkowski distance. So here we have ds squared equals dt squared minus dx squared minus dy squared minus dz squared. So a note, the conventions we're using here, the speed of light is equal to 1, and our signature, that is the signs as we see here, dt is positive, everything else is negative. So that's the example from special relativity. We have this ds, which tells us a way to determine the distance between 2 points, sort of. And then in GR, we have the same ds, except it's now not just one thing, but it's determined by this equation. So GAB is a 4x4 matrix, and so we have an equation to get ds squared from GAB. So in this case, we're going to look at what GAB would be for our special relativity equation. And what we see is that this is basically the identity matrix, except the dx squared, dy squared, and dz squared terms are -1 instead of 1. So the way we determine it in general is pretty simple. We just take each of the terms in the matrix and multiply it by the respective dx coordinates. And so here I've written that it's GAB times dxa times dxb, where xa represents t, x, y, z, so basically each of the 4 coordinates. In general, it's not necessarily a diagonal matrix, but it is always a symmetric matrix, and that's because we have commutative multiplication. So dxa times dxb is the same as dxb times dxa. So we're going to first start by looking at some diagonal matrices, and then we'll look at some that have off-diagonal entries as well, so you'll see examples of both. The important thing here, though, is that this matrix GAB tells you everything you need to know about the curvature of spacetime at a point. So basically, all of general relativity tells us that given GAB, we can figure out what spacetime is like. The next natural question is, okay, how do we get GAB? And that'll bring us to one of the 2 main equations of GR that describe the entire theory. This one is Einstein's equation, and it tells us a way to find GAB given the distribution of matter and energy locally. That distribution of matter and energy gets wrapped up into this other 4x4 matrix called the stress energy tensor. So the equation we have is very simple, actually. It's capital GAB equals 8 pi times g times TAB. So we're going to go through what this means individually. First, capital GAB is essentially a function of GAB and its derivatives. The details aren't important here. And then TAB is this thing called the stress energy tensor, which I said is a way to describe the matter and energy locally around that area. And I won't go into any details on how you compute this, but the important point here is it's some description of matter that you can get just based on knowing what's around there. And then finally, the capital G is just Newton's gravity constant, the one that Newton discovered hundreds of years ago. So nothing is new there. So in other words, we have to realize how important this equation is because we say lowercase gab is a function of just the distribution of matter and energy. And remember, we said that lowercase gab will tell us everything about the curvature of spacetime. And then another thing to note here is that this is a partial differential equation because capital GAB is a function of derivatives of GAB. So it's hard to get exact solutions. Uh, Most of the solutions are just numerical only, but we will go over a few exact solutions in this video. That brings us to the next major equation of GR, which is the geodesic equation. It's pretty simple. It just tells you if you have GAB, then what are the paths that the geodesics follow. So this form of the geodesic equation seems pretty daunting. One thing to note here is that gamma ABC is also another function of GAB and its derivatives. So this is yet another partial differential equation. And then we don't have to use this directly in this video, but it does describe the geodesics in more detail. What we will be using to put some restrictions on the geodesics that's much simpler is just looking at ds squared itself. So as we said before, ds squared is gab times dxa times dxb. The sum is implicit here. That's some of the notation of general relativity. Then we say if that ds squared is equal to 0, we call that null or light-like because that's what a photon does. If it's greater than 0, we call it time-like, and if it's less than 0, we call it space-like. And I'll give you examples of each of them. So if you look at this graph, we have on the x-axis, we have x, the position, and on the y-axis, we have time. So this 45-degree angle line has a slope of 1. Since we said c is 1, that's something following the speed of light. That's a photon. So that's why we call those light-like or null. The blue one is moving slower than light, so we call it time-like. Finally, this red path, we call it space-like. And space-like is not something, a space-like geodesic cannot be the path of any particle because it would have to be moving faster than light. With all that in mind, we can go to our first major example, which is the Schwarzschild metric. This is something that can be used to describe both a black hole and the gravity of the Earth. So it describes any system where the body that exhibits gravity has no significant charge or angular momentum. Although it requires it to have exactly 0, you can approximate. So Earth does rotate, but since the rotation is somewhat small in compared to its mass, we can approximate it by using this metric. And actually, if we do so, we recover Earth's gravity at the value that we expect it to be. So that is a good thing. We're going to look at the line element ds squared for this. It's a little more complicated than what we saw before. We're going to be using polar coordinates because this is spherically symmetric. So what we have here is 1 minus 2m over r times dt squared minus 1 over 1 minus 2m over r dr squared minus r squared times d theta squared plus sine squared d phi squared. Sine squared theta d phi squared. So what this is essentially if you ignore the 1 minus 2m over r term, you're going to recover basically the same Minkowski metric, that is the flat space metric that we saw before, except in polar coordinates. Now, we have to use this to figure out why do black holes suck you in. So you've probably heard of the event horizon. In the case of this black hole, it happens at r equals to 2 times the mass of the black hole. Of course, we're ignoring some units here, some factors of the speed of light, but that's essentially what it is. Here, the coefficient of dt squared, you can see it becomes 0 because 1 minus 2m over r is, of course, 0 in that case. We're going to examine what happens if we have a particle trying to escape the black hole. It's going to be trying to move straight away from the black hole, so it's not going sideways or up or down or anything. And we need it to follow a time-like or null path because it's either a particle or a photon. So we're going to rewrite the line element here, ignoring the d phi and d theta terms because they're 0, as we just said. And then we're just going to move everything over to one side and then take the square root of both and then divide by dt. and we get this value for dr dt equals 1 minus 2m over r. And so now we want that to be greater than 0 so that the particle is escaping. So what we get here, interestingly, is that r is greater than 2m. And remember, we just said r equal to 2m is where the event horizon is of the black hole. So this gives meaning to the event horizon. If something is within the event horizon, meaning if r is less than 2m, then the particle must fall into the black hole regardless of how fast it's going, because dr dt is negative. And now we can use the same kind of logic to examine a very interesting property of rotating black holes. Uh, this could also apply to any rotating body, but the properties we'll see require it to be dense enough to be a black hole, essentially. So we have another line element here. It's a lot more complicated because the angular momentum does change things quite significantly. Uh, we define two constants, rho squared and delta, which just make writing the equation much simpler. This form is called the Boyer-Lindquist form. So here's a diagram of the kind of anatomy of the rotating black hole. Pay close attention to this thing called the ergosphere. That's the surface we're going to be examining, which is it's an area outside the event horizon in which a particle here must rotate in the same direction as the black hole. So the event horizon is contained within the ergosphere, but there's a region just outside the event horizon where that property still applies. And so that's a very interesting thing because it's something you don't see with a non-rotating black hole. So now we're going to follow the same kind of argument like we did to show why particles get sucked into the event horizon, or once they're past the event horizon, they get sucked in towards the singularity. Now we're going to show if they're in the ergosphere, they have to rotate. So let's consider a photon trying to stay stationary, that is to escape this rotation, essentially, or even rotate counter to the black hole. It's going to be outside the event horizon, so it's not going to be falling into the black hole. So what we're trying to get here is saying that dr squared and d theta squared are both 0 because we don't want it to be moving up and down. We don't want it to be trying to go out. It's just trying to not rotate and stay stationary. So we're going to do some more manipulation here. Again, it's going to be more complex, but essentially we're doing the same thing. Get things on both sides, and then take the square root of both sides and move everything over again. And then eventually we're going to get to a value for d phi dt. What we're going to show is that d phi dt, if it's less than 0, then it must be outside the radius of what is called the ergosphere. So we're going to get to this form, a dt plus or minus delta to the 1/2 dt equals sine theta times r squared plus a squared d theta plus or minus delta to the 1/2 a sine squared theta d phi. And that allows us to just divide everything over and arrive at this value for d phi dt. So now recall what we're trying to do here. We want to find the values for which d phi dt is less than or equal to 0. That would mean it's rotating against the black hole or at least staying stationary. So we're going to take the negative sign in this equation. Both of them are valid solutions, but if you look at taking the positive sign, then it's clear that this is positive, and that corresponds to when the photon is moving in the same direction as the black hole. That's not what we're interested in here. However, if we do take the minus sign, what we see is that the denominator is still positive always, as long as r is more than 0. So if we want dr dt to be less than or equal to 0, then the numerator has to be negative. So what we're going to do now is examine what the conditions are for the numerator to be negative. And so we defined delta before as r squared minus 2rm plus a squared. Recall m is the mass of the black hole, a is the angular momentum of the black hole. And of course, these units have some factors of the speed of light and other constants as well, but that's not super important at this time. So we'll just move the delta term over to the other side, and then we're going to square both sides so we can use the quadratic formula. So we get a squared sine squared theta is less than or equal to r squared minus 2rm plus a squared. And this is where the magic will happen. So what's going to happen now is we can use the quadratic formula to solve for the values of r. And we want this to be, we want to find the values of r such that such that d phi dt can be less than or equal to 0. What we're going to get is that we're going to take the positive sign here in the quadratic formula because we said we're outside the event horizon. That was our condition here. So what we get is r greater than or equal to m plus square root m squared minus a squared cosine theta. And if you look at the diagram that we saw above, that was the radius of the ergosphere. So what we just showed is that if something is outside the event horizon and rotating against a black hole, it has to be outside the ergosphere. So that means on the contrapositive that if something is in the ergosphere, everything in the ergosphere has to rotate in the same direction as the black hole. So just to review what we just did here, we showed we considered the case of something trying to not rotate with the black hole, and we said if that's the case, it's not in the ergosphere. So therefore, if something is in the ergosphere, it must be rotating with the black hole. And now we're going to do a review of everything we've covered in this video. The first concept is that gravity is the same thing as just the curvature of spacetime, and that we can perceive everything that has to do with gravity through that lens. Next, we talked about geodesics, which tell us the curvature of spacetime by being the curved version of a straight line through spacetime. Then we went through Einstein's equation, which tells us how to get GAB from the stress energy tensor, which is the distribution of matter. And then we took our first example, which was the Schwarzschild or non-rotating black hole, and we looked at how, given this information, if you have something trying to escape, it must be outside the event horizon because everything in the event horizon inevitably gets sucked into the black hole. And that was because we showed in the event horizon dr dt is less than 0. And remember that in both of these cases, we restricted ourselves to time-like or null geodesics because we're interested in particles or photons, that is, things that actually exist, rather than something that moves faster than the speed of light, which could potentially escape from a black hole, but is not something we've ever observed. Next, we looked at our second example, which was a rotating black hole, also called the Kerr metric. And so what we did in that case was to examine the properties of the ergosphere. So we already know that in the event horizon it gets sucked in, so we didn't need to examine that again. So we looked at something outside the event horizon, that is something you could come back from, but inside this ergosphere, which was another radius contained outside the event horizon. We looked at a particle trying to remain stationary or rotating against it. We saw it couldn't do that if it's inside the ergosphere. So in the ergosphere, everything that is a particle or a photon, massive particle or a photon, must rotate in the same direction as the black hole.